Сейчас в Москве 10:30 утра, and we are happy to start our today's seminar. Our speaker is Natalia Vladimirovna Maslova, and she will tell us about Gruenberg-Kegel graphs and beyond. Let's welcome.
Okay, Vasya, many thanks for the invitation, Vasily, and I'm very happy to give a talk here. So, this talk is dedicated to the bright memory of Professor Otto Kegel, who has recently passed away. He was a very nice person and very deep and bright mathematician who has given us many bright ideas in group theory and in applications. And one of construction he introduced was so-called prime graph, Gruenberg-Kegel graph. And today the topic of my talk is about Gruenberg-Kegel graphs and beyond. So during this talk, any group is finite. And if we speak about graphs, these are simple graphs. It means undirected graphs without loops and multiply edges. And if we mention n-click, we keep in mind a complete graph on n vertices. All the edges exist. No loops, no multiple edges. And if we discuss n-click, it's empty graph on n vertices. It means just n vertices and no edges. If we mention an object, it can be any object you can keep in mind, for example, a graph, a crystal, a dynamical system, a network, a surface, anything you want. Then I give talks on seminars on algebraic combinatorics. I recommend to keep in mind a graph. Since here it's topological seminar, you can keep in mind surface, for example. What's about Gruenberg-Kegel graphs? The scheme is the following. If you take any object, then I'm sorry, this is my cat. He is co-speaker here. So if you keep in mind an object, you have its orthomorphism group. If you know orthomorphism group, then with this knowledge, you can have some new knowledge about the object itself. However, the situation then the orthomorphism group of an object is given in advance is very rare. So, very usual situation, then you have an object and need to construct an orthomorphism group. And this task is not simple. What's in the idea how to solve this problem? The idea is to take some arithmetical parameters of this group and try to construct the group using information about its arithmetical parameters. If this group can be uniquely determined by its arithmetical parameters, okay, it's success, we are happy, we have constructed the orthomorphism group of our object, and it's win. Otherwise, probably they need to add some other arithmetical parameters. I will provide examples. I think the situation will be clear after several minutes. First example, if you take very well-known Peterson graph, in algebraic combinatorics, if you have some conjecture, you need to check this conjecture first in Peterson graph, since the Peterson graph is a counterexample to many conjectures. So, as I know, in topology, in representation theory and so on, Peterson graph is also a very bright example. So let us start from the Peterson graph. We need to construct its orthomorphism group. Of course, we have exactly 10 vertices, so this will be a subgroup of symmetry group on 10 points. And you can, of course, you can find that there is a rotation and there is inversion inside inner cycle becomes outer cycle and inverse. And we can use the Fratini argument. Then the group is the product of a regular subgroup. A regular subgroup T was generated by this rotation and this inversion, and the point stabilizer. You can find the orders of the point stabilizer and the order of this group T. So we can easily prove that the order of this group is 120. And if you try to look to the graph, you can easily find that element orders of the homomorphism group of this graph are exactly 1, 2, 3, 4, 5, and 6. And there are no another element orders. This is not hard to find. So, and now what can we do with this information? Here we have special tool which was proved for us. Rolf Brandl and Wu Zhishi, 1991. If a finite group has order 120 and the element orders 1, 2, 3, 4, 5, and 6, then this group is exactly the symmetry group on 5 points. So we have proved that the homomorphism group of the Petersen graph is the symmetry group on 5 points. So I have just demonstrated techniques.
Excuse me, maybe you can use similar approaches to identify, say, the monster group or.
Yes, I will give examples. I will give such examples. You are completely right. What's about
so if order is 120 and element orders are 1, 2, 3, 4, 5, 6, then it's enough? Is it enough?
It's enough to prove that this group is exactly the symmetry group on 5 points. It's enough. It's group theoretical result. Now okay. I will introduce these techniques and introduce some results and approaches in this technique, and will demonstrate you how can we use this, for example, to define the monster group.
Oh, okay. Great.
If you take a fine set of integers, denote by pi of omega, it's the set of all the prime divisors of the numbers from this set. So we will call this set of primes the prime spectrum of this set. As an example, 2, 15, 21, and 35, the prime spectrum is 2, 3, 5, and 7. And let us construct a prime graph of this set. The vertices of this graph are exactly the primes from the prime spectrum of the set. And two vertices are adjacent if and only if their product divides some element from the set. For this set, 2, 15, 21, and 35, the prime graph will be the union of two cliques. One consists from the only vertex 2, and another one is 3, 5, and 7. So it's the prime graph, and you can easily find if you take some set and close it under taking divisors, the prime graph will be the same. So we can keep in mind that our set is closed under taking divisors. What about groups? If you take a finite group, the spectrum of this group is the set of all its element orders. If you have a finite group, then there is a finite number of elements, and each element has finite order. So the spectrum of a finite group is a finite set of numbers, of integers. And of course, it's easy to prove that it's closed under taking divisors. This prime spectrum of a finite group G is the set of prime divisors of the order of the group. It's the same that the set of all prime divisors of element orders of the group. And it's the same that all the primes from the spectrum. You can easily prove it. And what about the prime graph or the Gruenberg-Kegel graph or GK graph, like Peter Cameron likes to tell it? It's a simple graph on the set of prime divisors of the order of a finite group, such that two primes are adjacent if and only if their product is an element order of this group. So it's clear that the Gruenberg-Kegel graph defined on the group is exactly the prime graph defined on the spectrum of this group. And you can easily prove it's an easy exercise. Two primes, P and Q, are adjacent in the prime graph, in the Gruenberg-Kegel graph of a finite group, if and only if there are elements X and Y of G such that they commute and their product are exactly P and Q. And if the graph is disconnected, then we denote by pi1 of G, pi2 of G, and so on, its connected components. And if the group has even order, we assume that P, that 2 divides to the first connected component of the group. Just for simplicity, 2 belongs to the first connected component. We re-enumerate if you need. The concept of Gruenberg-Kegel graph appeared in unpublished manuscript by Carl Gruenberg and Otto Kegel. And really, they have introduced it as a legend. It was one of conferences, and they discussed this concept during the coffee break. And in first time, the definition of Gruenberg-Kegel graph was written on the towel by a pen. So one of very important applications, and one of the first applications, the argumentation ideal of an integer group ring is decomposable as a model if and only if the Gruenberg-Kegel graph of this group is disconnected. And of course, since this application, connected components of Gruenberg-Kegel graph of finite simple groups were described by Williams. He is a student of Carl Gruenberg, and this investigation was finished by Anatoly Kondratiev, who was my supervisor by PhD. And the Gruenberg-Kegel theorem was not published by Carl Gruenberg and Otto Kegel, but Williams has added this theorem to his
And
manuscript.
do we have Gruenberg-Kegel graphs for other algebraic structures?
Yes. There are similar constructions for other algebraic structures, but for groups, it's a very useful tool. Now, I will give some common picture of the Gruenberg-Kegel graph of a group, and then we can discuss some applications. And of course, there are some similar constructions like Gruenberg-Kegel graph for our algebraic constructions. Okay, what about examples? There are distinct groups with the same spectra. Of course, symmetry group on 5 points and on 6 points has the same spectrum. We have groups with distinct spectra, but with the same Gruenberg-Kegel graph. For example, alternating groups on 5 and on 6 points. Moreover, the alternating group on 5 points is uniquely determined by its spectrum. However, the alternating graph on 6 points is not uniquely determined by the spectrum. As an example, there are groups such that the Gruenberg-Kegel graphs are isomorphic like unlabeled graph, but not equal like labeled graphs. For example, if you take the alternating group on 10 points and the orthomorphism group of the second Janka group, then the Gruenberg-Kegel graphs are isomorphic like unlabeled graphs. Moreover, their prime spectra coincide, but the graphs themselves are not equal. And they call a finite group recognizable by spectrum or respectively by Gruenberg-Kegel graph if it's uniquely determined by its parameters in the class of finite groups. K recognizable if there are exactly K pairwise non-isomorphic groups with these parameters. Almost recognizable if it's K recognizable for some positive integer K, for example, and unrecognizable if there are infinitely many pairwise non-isomorphic groups with the same parameter as our group, with the same graph or with the same spectrum, respectively. So any group is either recognizable or almost recognizable but not recognizable or unrecognizable. There are three cases, and each recognizable group is, of course, almost recognizable. What's about recognition by spectrum? There was a very, very bright result by Professor Viktor Mazurov from Novosibirsk and by Professor Wu Zhishi from Chunцин University, it's China. They have proved that a finite group is unrecognizable by spectrum if and only if there is a finite group with non-trivial solvable radical such that its spectrum coincides with the spectrum of our group. And of course, if some group is recognizable or almost recognizable by spectrum, from this theorem it follows that its solvable radical is trivial. In particular, the question of recognizability of recognition by spectrum is interesting for finite simple groups. Let me remind the result.
Can I see the second condition? If there is an H such that?
There is a finite group such that it has a non-trivial normal solvable subgroup. Equivalently, has a non-trivial normal abelian subgroup. Equivalently, its solvable radical is non-trivial. Solvable radical is the largest solvable normal subgroup of a finite group. Do you need some extra comments here? Since this topic is not very close to topology. Okay. What's about finite simple groups? Let me remind some results. A finite group is simple if it doesn't contain proper normal subgroups. And the finite group is almost simple if there is a non-abelian finite simple group such that this group is between the inner homomorphisms of this group and all the full group of homomorphisms of this group. It's easy to prove that a finite simple group, a finite non-abelian simple group is isomorphic to the group of its inner homomorphisms. And if a group is between a finite simple group and the full homomorphism group of this group, then this group is called almost simple. And finite non-abelian simple groups are classified. The classification was announced in 1980, and it really was completed around 20 years ago. And with respect to this classification, finite non-abelian simple groups are alternating groups, classical groups. These are groups which has very good matrix representations. Exceptional groups of Lie type, you can see 10 families of exceptional groups of Lie type and 26 sporadic groups. So with all the classification, well-known monster group is one of these 26 sporadic groups. I will mention the results for monster group separately. About recognition by spectrum, there is a very strong result which we can formulate as follows. Almost all finite simple groups are almost recognizable by spectrum. Moreover, each finite non-abelian simple group is uniquely determined by the pair of its parameters, the spectrum on the order. It's exactly the situation then I mentioned. We need to add some extra parameter. in some cases, the spectrum is not enough, but if you add the order of this group, then it will be enough to uniquely determine this group. What about other results on recognition by spectrum? There are almost simple but not simple groups which are recognizable by spectrum. For example, symmetry groups of large dimensions. There are examples of groups with non-simple circle which are recognizable by spectrum. One of such examples was constructed by Victor Mazur. It was first example of group with non-simple circle, which is recognizable. The circular group is a group which generated by the minimal normal subgroups.
Okay.
The circle. Okay. If a group is almost simple, it contains exactly one minimal normal non-abelian fine simple subgroup. And if group has non-simple circle, then it's not almost simple. The direct square of the Suzuki group of the field of 2 power 7 is recognizable by spectrum. The second example was constructed by Ilya Gorshkov and me. You can see more than 20 years later. The direct square of the fine simple sporadic Yankov fourth group. And there are some other results. And very important result by Yan Nanin from China, Ilya Gorshkov, Alexey Staroletov, and Andrei Vasilyev from Novosibirsk. For each natural number k, there exists a fine simple group G of k such that the direct Kf power of this group is still recognizable by spectrum. So the spectrum is a very powerful parameter of a fine group. What about recognition by Gruenberg-Kegel graph?
By the way, we can ask about other parameters, not only orders of elements, but for example, dimensions of presentations. So we can ask.
Yes,
for example,
of course.
When we talk about the monster groups, usually one talks about dimensions of its representations.
Yes, of course. There are also such results. These results are off top of this talk, but of course there are another constructions, another arithmetical parameters such that we can investigate, and there are another very nice results about recognition by another types of parameters, other types of parameters. You are completely right. About Gruenberg-Kegel graph. Of course, if you have groups with the same spectra, then the Gruenberg-Kegel graphs will coincide. However, if you take distinct groups with the same Gruenberg-Kegel graph, they can have distinct spectra. I have given such example. So for recognition by Gruenberg-Kegel graph, 4 years ago, they have proved, me and Peter Cameron from the United Kingdom, they have proved that for recognition by Gruenberg-Kegel graph, exactly the same criteria holds. A fine group is unrecognizable by Gruenberg-Kegel graph if and only if there is a fine group with non-trivial Sobel radical such that the Gruenberg-Kegel graphs coincide. From 2 to 1, of course, it's a direct corollary from the Mazurov-Shi theorem. However, from 1 to 2, it's rather non-trivial fact. But in the case of Gruenberg-Kegel graphs, in contrast with the spectrum, we have a very powerful corollary of this criterion. If a fine group is K-recognizable, is almost recognizable by Gruenberg-Kegel graph, then this group is almost simple. Each group with the same Gruenberg-Kegel graph is also almost simple. The vertex 2 is non-adjacent to at least one odd prime in the Gruenberg-Kegel graph. And the graph have at least 3 pairwise non-adjacent vertices. And as a corollary, a group G is almost recognizable by Gruenberg-Kegel graph if and only if each group with the same Gruenberg-Kegel graph is almost simple. So for the case of recognition by Gruenberg-Kegel graph, this is very, very well-defined problem. Why is it interesting? Why is it interesting to try to recognize almost simple groups by something? Why is the class of almost simple group is important? If you take any object, of course, you can have its homomorphism group, it's a subgroup of symmetry group, for example, on parts of its object. As an example, I have given Peterson graph. Its homomorphism group was a subgroup of symmetry group on 10 points. Assume all the objects, all the groups are fine. How can we define G? First of all, we can see to the orbits of a symmetry of the homomorphism group, and then this group will be the subdirect product of subdirect product of groups, symmetry groups on these orbits. In this sense, we can assume in advance then that G is transitive, since otherwise we can just look to its orbits. So next we need to look to in primitive systems. I mean, we need to try to find partitions which are invariant under the action of the group. And if we look to the maximal possible partition, then the group will be so-called primitive on parts of this partition. So in some sense, the question of finding the homomorphism group can be reduced to primitive permutation groups. But primitive permutation groups were described very well by Martin Liebig, Cheryl Prager, and Jan Saxel. And they have either well-defined so-called geometrical representation or are almost simple. So almost simple groups are very, very important for permutation groups. It's a very important class of fine groups. And it's really interesting to try to recognize these groups by arithmetical parameters, since otherwise we can have some geometrical representation. We can use features of these well-described actions. And in the case of almost simple groups, we need some extra information, and the recognition techniques is a very good tool in this sense. So what is a summary? Almost all fine simple groups are almost recognizable by spectrum, and there are many non-simple groups which are recognizable by spectrum. And if a fine group G is recognizable by Gruenberg-Kegel graph, then it's of course recognizable by spectrum. The converse does not hold in general case. But computing the spectrum of a group is not easy. Computing the Gruenberg-Kegel graph is much more easier. And if an almost simple group is recognizable, if a fine group is almost recognizable by Gruenberg-Kegel graph, then this group is almost simple. However, the class of almost simple groups is a very, very important class of primitive permutation groups. So it's summary, why is it interesting? And the example about the monster group. You can see the monster group is the largest fine simple sporadic group. Its order is huge. However, its Gruenberg-Kegel graph has exactly 15 vertices, and it's very well visible. So you really can try to represent a fine simple sporadic group monster by its Gruenberg-Kegel graph. And really, if you need to send the information about the monster group to another galaxy, then you can just define a fine group. You can define the element order, the order of the group, the Gruenberg-Kegel graph, and print this picture and send this information to another galaxy. And really, in this case, you have sent all the information which you need to define the monster group. So, what about the picture with small groups? For example, there are
What about monstrous moonshine conjecture studied by portraits?
This is a little bit another question. It's a question how to define a huge group by something simple.
What can we say? Can we say that, for example, this group acts on something? So if we have Z2 and Z3, then probably we have some three-element permutation. And then we have some other subgraphs in the Gruenberg-Kegel graph, then possibly we should have some other actions on something else.
Really, then you have the information about the Gruenberg-Kegel graph is important more in sense that there are no such edges. For example, there are no edges 29 and 71, for example. And it gives more information that then there exists an edge. I'm sorry, probably I have not understood in details all your question, but the information that there is no an edge is more important.
No, I mean, if we have a certain subgraph of the Gruenberg-Kegel graph, can we guarantee, for example, that this group does act or does not act?
No. If you have a subgraph, you cannot guarantee that it's a graph of some subgroup. If you take some subgraph, probably there is no subgroup with such a graph. For solvable groups, it has sense. However, for non-solvable groups, and especially for fine simple groups, if you have an arbitrary subgraph, probably there is no subgroup with such a subgraph. However, if you take a subgroup, of course, its graph will be a subgraph of the graph of the group. However, inverse doesn't hold.
Okay.
The situation is more and more complicated. What about small groups? There are exactly 55 fine simple groups with prime divisors of the order at most 15. About recognition by spectrum. 36 of them are recognizable by spectrum. 7 are too recognizable. And 12 are unrecognizable. And what about recognition by Gruenberg-Kegel graph? 5 are recognizable. 2 are 6 recognizable. 3 are 3 recognizable. 5 are 5 recognizable. And 38 are unrecognizable. So the picture for recognition between Gruenberg-Kegel graph and the spectrum is very, very great, very, very big. As I have mentioned in advance, the problem of recognition by Gruenberg-Kegel graph is very well defined. It means that if we solve this problem for almost simple groups, then they will solve this problem at all. For each group, we can tell is it recognizable or almost recognizable or unrecognizable by Gruenberg-Kegel graph. So we have problem 1. Decide whenever I find almost simple group recognizable or almost recognizable or unrecognizable by Gruenberg-Kegel graph. You can find 2 papers here. One is by me and Peter Cameron in Journal of Algebra. Another is my survey paper in the proceedings of the World Meeting for Women in Mathematics. 4 years ago, I was an invited speaker of this event. It was a satellite of the International Congress of Mathematicians. So I was an invited speaker, and I was invited to submit a survey paper after my talk. And here, in these 2 papers, you have rather good surveys of known results about this problem. And one another problem is describe almost simple groups such that the vertex 2 is non-adjacent to at least one odd vertex in the Gruenberg-Kegel graph of this group, and the graph has at least 3 pairwise non-adjacent vertices. These groups are candidates to be almost recognizable. So to solve problem 1, firstly we need to solve problem 2. And the problem is much more easier when the graph is disconnected. Why is it true? I have mentioned the Gruenberg-Kegel theorem. Each finite group with disconnected Gruenberg-Kegel graph is either a well-defined Frobenius group, or a well-defined two-Frobenius group, or an extension of some nilpotent group by some almost simple group. So there are this is a very, very strong tool to use in the case when the Gruenberg-Kegel graph of a group is disconnected. When the graph have many connected components, then it was conjectured by Viktor Mazurov. If a finite simple group such that its Gruenberg-Kegel graph has at least 3 connected components, which is not isomorphic to the alternative group on 6 points, is recognizable by spectrum. It's true. It was proved by Anatoly Kondratyev in 2020, and really the problem of recognition by spectrum was completed for all finite simple groups with disconnected Gruenberg-Kegel graph. If this is a recent preprint by Viktor Palchin from Novosibirsk, but in connection of the Mazurov conjecture, there is problem 1 prime. If G is a simple group such that its Gruenberg-Kegel graph is disconnected, then decides whenever this group is recognizable or almost recognizable or unrecognizable. And if the number of connected components of the Gruenberg-Kegel graph is at least 3, then the list of this group is known. For many of them, the problem was solved. For alternating group, there are partial results. For group PSL2Q, the results were obtained. However, they have mistakes. My PhD student, Kristina Ilenko, had ruled out this problem, and now she is working on her paper. I think it will appear rather soon. And the question was opened for find simple exceptional groups of Lie type with at least 3 disconnected components of Gruenberg-Kegel graphs. So I will skip some details. Here it's some history. The presentation will be available if somebody is interested. I think it's not hard to find this presentation. But we have completed this question. Every finite simple exceptional group of Lie type, which is neither a Suzuki group nor G2-free exceptional case, is almost recognizable by Gruenberg-Kegel graph. However, these groups are unrecognizable. What about another results about groups with disconnected Gruenberg-Kegel graph? Find simple exceptional groups of Lie type E6 or twice E6 are almost recognizable by Gruenberg-Kegel graph. And find simple groups F4Q, find simple exceptional group F4Q from this series, where Q is special, are also almost recognizable by Gruenberg-Kegel graph. These are rather recent results. I think papers will appear very soon.
Excuse me, can I see the formulation again? Q is odd, Q is not. Q is
Q is
0.
not plus minus 1 modulo 5. Q is not plus minus 1 modulo 5.
Okay.
It's a technical question. I think we will complete with all the cases. What about the question of recognition of affine group with connected Gruenberg-Kegel graph? There is a very strong result by Andrei Vasilyev. If we take a non-solvable group such that 2 is non-adjacent to at least one odd prime in the Gruenberg-Kegel graph, then the factor group of such by solvable radical of such a group is also almost simple. So let me remind, if our group is a candidate to be almost recognizable by Gruenberg-Kegel graph, we have already proved that 2 is not adjacent to at least one odd prime in the Gruenberg-Kegel graph of this group. So we can use the question that 2 is non-adjacent to at least one odd prime. And then the factor group of such a group by its solvable radical is almost simple. So we can use this technique, and in the condition of the I'm sorry.
Yes, please go on.
I'm sorry, I was forced to reply the telephone call. And in the conditions of the previous theorem, exactly one of the following statements holds. Either all the primes which are adjacent, non-adjacent to 2 belongs to the prime spectrum of the solvable radical, or all these primes belong to the prime spectrum of these non-abelian composition factors. And in particular, a very, very important condition for the Gruenberg-Kegel graph of any fine group that all the vertices which are non-adjacent to 2 in the Gruenberg-Kegel graph form a union of cliques. It's a very, very important tool for us. And then we try to describe how many choices can we have for fine groups with Gruenberg-Kegel graph as our group. If we take any graph, we will call this graph as a labeled graph if its vertices are labeled by pairwise distinct primes. And me and Peter Cameron, we have proved that if we take a labeled graph, that there are infinitely many groups such that their Gruenberg-Kegel graph coincides with our labeled graph if and only if there are at more than the value of function on the number of the vertices of this graph groups, such that the Gruenberg-Kegel graphs coincide with this Gruenberg-Kegel graph. And we have proved that we can take as a function some polynomial of degree at most 7. However, this is not the best possible value, the best possible power, and it was improved by Maria Grechkoseyeva and Andrei Vasilyev. They have improved the function up to a polynomial of degree at most 5. However, I think it still can be improved. But due to a result by Andrei Zavarnitsyn, this polynomial cannot be a constant. In contrast to the previous case, these are almost simple groups with pairwise coincide Gruenberg-Kegel graphs. And in a very well-known list of unsolved problems in group theory called Kaurovka notebook, there is a problem established by Andrei Vasilyev. He has conjectured there are at most 4 fine simple groups, pairwise non-isomorphic fine simple groups, such that the Gruenberg-Kegel graph coincide. Here there is some list of results in this direction. If one of group is some office uninvestigated the situation, then Gruenberg-Kegel graphs of two fine simple groups coincide. If one of these groups is sporadic, then it's a result from Minahagi, by Minahagi from Japan. And if one of groups is alternating, it's a result by Maria Zvezdina from Novosibirsk. And the cases of coincidence of Gruenberg-Kegel graphs of fine simple groups were described by Mariana Zinovieva, who is my colleague, and she was a student. She has defended her PhD with the same supervisor as me. So it's called my scientific sister. These were results by Mariana Zinovieva. I think she will give a detailed talk in this March about her results. And let us skip labeling on the graph. We will call a fine group recognizable by isomorphism type of its Gruenberg-Kegel graph. If and only if the group is the graph of another group is isomorphic as extra graph of our group, if and only if the group is isomorphic to our group. If you remember, I have mentioned, I'm sorry, I will demonstrate you the example. Here we have groups such that their graphs are isomorphic but not equal. Then we try to recognize by Gruenberg-Kegel graph. We recognize by labeled Gruenberg-Kegel graph. But we can skip labeling and try to recognize just by isomorphism type of its Gruenberg-Kegel graph. So a group is recognizable by isomorphism type of its Gruenberg-Kegel graph if for each group H, the graphs of groups H and G are isomorphic as abstract graphs, if and only if the groups are isomorphic. Of course, if a fine group is recognizable by isomorphism type, then it's recognizable by Gruenberg-Kegel graph. And of course, by theorem 2, it's almost simple. And here we have a problem defined whenever a fine group, almost simple group, is recognizable by isomorphism type of its Gruenberg-Kegel graph. In this direction, there are no so many results. The first example was the fourth Yanka fine simple sporadic group constructed by Andrei Zavornitsyn. This group is the only fine group which has 6 connected components of its Gruenberg-Kegel graph. Me and Peter Cameron have proved that these exceptional groups of Lie type EH2 and twice G227 are recognizable by isomorphism type of Gruenberg-Kegel graph. And for all fine simple sporadic group, the question was solved by Thomas Popel and Melissa Lee from Australia. And our recent result with Minju Chen, it's my Chinese colleague from Hainan University, and with Mariana Zinovieva, we have proved that the fine simple exceptional group EH2 is uniquely determined by isomorphism type of its Gruenberg-Kegel graph. Its Gruenberg-Kegel graph is printed in the picture. You can see it's rather small and nice. And also the groups EHQ for another Q, 3, 4, 5, 7, 8, 9, and 17 are also recognizable by isomorphism types of Gruenberg-Kegel graphs. And
So what is, excuse me, so is it, can you show the previous slide?
Yes.
So this is only for 2e6.
Yes, the question of recognition by isomorphism type of Gruenberg-Kegel graph is really much more hard than the question of recognition by Gruenberg-Kegel graph itself. There are really no many examples of groups which are recognizable. If you can check 1, 2, here 8, 10, 11, 12, 19 examples. Now, at the moment, there are known 19 examples of fine groups which are recognizable by isomorphism type of Gruenberg-Kegel graph. There are no other results. And the question is an almost simple but not simple group which is recognizable by isomorphism type of Gruenberg-Kegel graph? And is the number of such groups is finite or infinite? There are no exactly 19 examples. Is there an infinite series of groups which is recognizable by isomorphism type of Gruenberg-Kegel graph? What's about Gruenberg-Kegel graphs and graphs defined in groups? In contrast to the previous case, they can define a graph not on the prime divisors of the order, but on the group itself. If we take T of G to be a graph defined on a group G, and if the adjacent criteria is the two elements are adjacent if and only if they commute, then this graph is called the commuting graph. The power graph, two elements are adjacent if and only if one of them is a power of another. Enhanced power graph, two elements are adjacent if and only if the subgroup generated by these elements is cyclic. A deep commuting graph, the inverse images of G and H commute in every central extension of the group. So, distinct kinds of graphs defined on group itself. I remind, a graph is a cograph if it can be built from one vertex graph by the operation of disjoint union and completion. And it's well known that a graph is a cograph if and only if it forbids a path of length 4. Let us discuss some questions of graph defined on groups, and then let us demonstrate how to rule out the problems of graph defined on groups via Gruenberg-Kegel graph and similar graphs. Recently, they have proved that a finite group such that its commuting graph is a cograph is very close to solvable group. Either it has a condition which is close to be solvable, or have exactly one non-abelian composition factor. I will provide you a reference if you. I don't think that it's a good idea to discuss many details here. I will provide a reference. However, here the sense of this example is that the properties of graphs defined of groups have very strong impact on the group structure. And how can we rule the question about graphs defined on groups with using Gruenberg-Kegel graphs? For a finite group, let T of G denote one of 4 types: commuting graph, power graphs, enhanced powered graph, deep commuting graph, and so on. If graphs of the same type of 2 groups are isomorphic, then Gruenberg-Kegel graphs of which graph are equal. So, if some group is uniquely determined by its Gruenberg-Kegel graph, you can see that it's very strong condition for graphs defined on groups. And for a finite group, the following conditions are equivalent. Enhanced power graph is equal to power graph. The Gruenberg-Kegel graph of G doesn't have edges. And using this condition, G is a known group. We can easily describe all these cases. So, Gruenberg-Kegel graph is a very, very important tool to rule out problems with graphs defined on groups. And another application, if you take a subnormal graph Subnormal graph is a directed graph on a group such that two vertices H and Y are adjacent. There is an arc from H to Y if a subgroup generated by X is a subnormal subgroup in the subgroup generated by X and Y. The standard question whenever this graph is strongly connected. And we can prove that this graph is strongly connected if and only if the corresponding graph of the factor group by hypercenter is strongly connected. So we can assume that the hypercenter of the group is identity. And it's not hard to prove that if the hypercenter is identity and G is neither a Frobenius group nor almost simple, then it's some subnormal graph is strongly connected. For Frobenius group, it's easy to prove that its subnormal graph is not strongly connected. What's about almost simple group? We define the prime fitting graph. It's very similar to Gruenberg-Kegel graph. The vertex sets are the prime divisor of the order of the group, and there is an arc from P1 to P2 if there is a subgroup of this group such that the product of P1 and P2 divides the order of this subgroup, and P1 divides the order of the fitting subgroup of this group. The fitting subgroup is the largest normal nilpotent subgroup. So if this graph is not strongly connected, the prime fitting graph, then the subnormal graph is not strongly connected. It's easy to prove. So the question is to classify the strongly connected components of prime fitting graphs of almost simple groups. What's about Gruenberg-Kegel graph? If two vertices are adjacent in Gruenberg-Kegel graph, of course, these two vertices are strongly adjacent. I mean, there is an arc from the first to the second, and an arc from the second to the first in the prime fitting graph. So the question is very similar to find connected components of Gruenberg-Kegel graph of a fine group. And we can use results by Williams and Kondratiev for connected components of connected components for Gruenberg-Kegel graphs of fine groups. This result is still in progress. I think we will complete this very soon. And what's about Gruenberg-Kegel graphs and graphs with regularity conditions? Maria Silva Lucido has proved that if the Gruenberg-Kegel graph of a fine group has an indust-Fricka-Click, then the group is non-solvable. And around 10 years ago, 5 mathematicians from the United States, Alexander Gruber, Thomas Keller, Mark Lewis, Kelly Norton, Benjamin Strasser proved that if we take a simple graph, then this graph is isomorphic to the Gruenberg-Kegel graph of a solvable group, if and only if the complement to the graph is free colorable and triangle free. It's very combinatorial condition. So I have written to Kauraka notebook the question, is there a non-solvable group such that its Gruenberg-Kegel graph doesn't contain Fricka-Clicks and is not isomorphic to Gruenberg-Kegel graph of any solvable group? And an example of such a group cannot be almost simple. We have proved it several years ago, and we proved it with Ilya Gashkov several years ago. And let us remind, by the Fein-Thompson theorem, each group of odd order is solvable. And if G is of odd order, then its complement is free colorable. However, recently, me and Ilya Gashkov and Minju Chen from Hainan University and Nanin Yang have proved that if G is a group of even order, such that tau is the set of vertices which are non-adjacent to 2 in the Gruenberg-Kegel graph. And then if its set is not empty, then I have already mentioned this is the union of cliques. It's very, very strong combinatorial condition, and we can use this. For example, we can use it to classify strongly regular graphs which are isomorphic to Gruenberg-Kegel graphs of fine groups. What's a strongly regular graph? A graph is k-regular if each vertex has degree k, and is strongly regular if it's with parameters vk, lambda, mu, if the graph has exactly v vertices, is regular of degree k, and each two adjacent vertices has exactly lambda common neighbors, and each two non-adjacent vertices has exactly mu common neighbors. Around 10 years ago, Jack Cullen, he is a very good specialist in algebraic combinatorics from Netherlands. Now he lives in China and in the University of Science and Technology of China. He has asked me, what are strongly regulars which are isomorphic to Gruenberg-Kegel graphs of fine groups? Why is it important to investigate strongly regular graphs? Here it's some preface from the paper from the book by Andrews Browen and Helmut van der Maldenwener about strongly regular graphs. These are really very important objects which appear in group theory, in geometry, in coding theory, in cryptography, anywhere. So we were able to prove that me, Minzhu Chen, Gashkov, and Nanin Yang, we have proved that a strongly regular graph is isomorphic to the Gruenberg-Kegel graph of a fine group. If it's isomorphic, then either this graph is the complement to a triangle-free strongly regular graph, or this graph is a complete multipartite graph with all the parts of size 2. And the number of parts is unbounded. We can easily find an example for each number of parts. And in statement 1, if the complement of this graph is free colorable, then there is a solvable group with such a graph. But if not, the existence is not known. So the partial case of problem H is the strongly regular graph such that gamma is triangle free and is not free colorable, and the complement of gamma is not isomorphic to the Gruenberg-Kegel graph of any solvable group. And to classify strongly regular graphs which are isomorphic to Gruenberg-Kegel graphs of fine groups, it was necessary to rule out the situation then a complete multipartite graph is the Gruenberg-Kegel graph of a fine group. So it was necessary to prove that if we take a complete multipartite graph with each part of power at most 3, then this graph is not Gruenberg-Kegel graph of any fine group. A partial result was obtained by me and Dusan Pagon 10 years ago for complete multipartite graph. And the common result was obtained by Minzhu Chen, me, Ilya Gashkov, and Nanin Yang. So we have done. And here there are some references. It's a paper by Arvind, Cameron, Ma, and me about commuting graphs published recently in Journal of Algebra. I think, as I remember, it's open access, it's available. A paper by me and Peter Cameron, also in Journal of Algebra. Our paper about combinatorial properties of Gruenberg-Kegel graphs. I recommend to look to the preprint by me and Minju Chen. It's available on Archive, and there is a survey paper which is accepted for proceedings for World Meeting for Women and Mathematics. It's also available on Archive, and our recent paper with Lev Nechitailo, who was a student of Moscow Technical University, and now he is employee of High School of Economics in Moscow. This paper is available also online, so I recommend to look it. And about seminar friendship, everybody is welcome to the Ural seminar on group theory and combinatorics. We work every other week on Tuesday. To attend the seminar, it's necessary to register on the seminar website. All the links to talks will be sent by email for registered participants. So everybody is welcome, and thank you for your attention. This is a
Thank
picture.
you very much. Yeah, thank you very much for a great talk. So are there any questions or comments? Maybe Mariana can give some comments concerning your joint work.
I'm not sure that Mariana can attend now.
Oh, she's here. She's here.
She's here. I'm
Yeah.
happy.
No comments so far. No questions so far. Well, we have a huge amount of papers we can look at, and actually we have yet another project, not only seminar friendship, but we have a project reading papers together. For example, recently I enjoyed reading Borchert's papers. Of course, I don't understand many things, but it was beautiful. I mean, monstrous moonshine. And it would be great if people from different parts of mathematics can do something together, not just writing joint writing, but for example, reading or organizing seminars, whatever else. Okay, that was a great talk. Maybe any questions? Well, anyway, the seminar is recorded, and I think Son John may share this recording with Natalia as well. But it will appear on our site, ktrt-seminars. Okay.
Thank you very
Okay,
much.
so thank you very much. It was really a very nice talk. Okay.